fourth application of Gauss's theorem. Fourth application of Gauss's theorem, electric field due to a uniformly charged thin spherical shell. Introduction is, consider a thin spherical shell of radius capital R with a uniform surface charge density sigma coulomb per meter square. What is sigma coulomb per meter square means?
Charge per unit area.
For each
Charge per unit area.
there is sigma coulomb. Each meter square, 1 meter square area if you take, there will be sigma coulomb of charge. If the surface charge density is 5 microcoulomb per meter square, means if you take 1 meter square area, there will be 5 microcoulomb. Okay, let Q be the capital Q. Let Q be the total charge on the surface of the shell. Then Q equal to, next line, Q equal to, can you tell what will be Q equal to? Surface charge density on the surface is sigma coulomb per meter square. If R is the radius of this one, sigma into 4 pi R square. So total charge Q is, you have to write down this equation. Therefore Q is equal to sigma into 4 pi R square. 4 pi into capital R square. Capital R is the radius of the spherical shell. See, in the case of the sphere, we have a uniformly charged spherical shell. This is the spherical shell. It is having sigma coulomb per meter square charge density. Capital R is the radius. Now we need to find out the electric field intensity at a point outside the sphere, somewhere here. Okay, at a point outside, this side or this side, any point outside the sphere. That is case 1. Second case, we need to find the electric field intensity at a point on the surface of the shell. The third case is to find the electric field intensity at a point inside the shell. It is a spherical one. It is just like a football. Okay, we have a point P here, and that point P, it is at a distance r from the small r from the center of the sphere. Means if you take the distance from the center of the sphere toward this point P, that distance is small r. Okay, this is small r, and this original sphere is having radius how much?
Capital R.
Metallic shell that is having radius capital R.
Yes, sir.
What is our aim here? And at the point P here, this is the point P, it is at a distance small r from the center of the shell. There will be some electric field here. How much is the electric field intensity that we have to calculate? We will consider this electric field intensity at this point as E. Suppose it is E. We need to find out an equation for this E. What is E value? What is the magnitude of E? That is the problem here that we have to solve by using Gauss's theorem. Got it?
Yes, sir.
Yes, sir.
Now, Adnan,
Gaussian spherical.
Gaussian spherical. Here already the original charged shell is spherical. It is a spherical shell. So we can consider another shell, okay, surrounding this shell, which is imaginary shell. It is drawn in such a way that its radius is equal to small r, and the point P should lie on its surface. It is drawn like this with a common center. Both the shell should have the same center. This outer one is imaginary, and that point P is at a distance r away from the center, and the point P lies on its surface, so that the r distance of the point P is the radius of the imaginary sphere. Okay. Now, suppose if I consider on this imaginary sphere an elementary area ds. Suppose I am taking a small area surrounding the point P, that is ds area. This area I am taking as ds. The point P is at the middle of this ds area. It's an infinitesimally small area, and this area vector for ds will be radially outward, and the area vector is radially outward like this. Okay, and this represents ds. So what will be the direction of electric field intensity on this imaginary Gaussian surface if you take any point? Because it is uniformly charged with the positive, electric field intensity or field lines, flux lines will be passing radially outward. So if I draw the flux lines or field direction, it will be this way at this point. This is the direction of electric field here. And if I take this point, this will be the direction of electric field. Everywhere it will be radially outward. And for this ds area at this point of P, that will be along this radius direction. If a point is taken this here, that will be this way. This all represent the direction of electric field intensity at the respective points. Got it? Then my question is again, what is then theta here? At this point P, ds is this way, normal to the surface ds, vector area is this direction. Electric field also in that same direction. Electric field intensity also in the same direction. So theta equal to what?
Theta
0.
So cos 0 equal to 1.
1.
And same is the case if I take ds area on this imaginary Gaussian surface. If I take ds area here, anywhere on this imaginary surface, everywhere ds will be radially outward, electric field also will be radially outward. At this point ds will be this direction, electric field also this direction. So at every point on the imaginary surface, theta will be equal to 0, cos 0 equal to 1. That point is clear?
Yes, sir.
Okay.
Yes,
The
sir.
next point is inside this Gaussian surface, inside this imaginary Gaussian surface, what is the total charge inside? What is the total charge inside this Gaussian surface? Q equal to.
Capital R square.
Got the point?
Yes, sir, I
So-
already said that.
So all of you remember, don't be confused in exam. There are two radius here. Capital R is the radius of the original spherical shell, which is charged with positive, sigma coulomb per meter square. Got it? Small r is the radius of an imaginary sphere, that is Gaussian sphere. It is only an imagination. There are no charges on this imaginary. This charge is lying inside this. Okay, the charge is lying inside the imaginary sphere. On the surface of imaginary sphere, charges cannot exist because it is only an imagination. Don't be confused, okay?
Yes.
So these are the basic concepts needed for solving this problem. Okay, now we can derive this one. What is the equation? First equation by Gauss's theorem. Phi equal to 1 by epsilon naught into Q. The total flux coming out of any closed Gaussian surface is equal to 1 by epsilon naught into the net charge inside that. This equation you take as equation number 1. Now first we will find out the total flux of this Gaussian spherical surface. First we have to find out the total flux coming out of this imaginary Gaussian spherical shell or imaginary Gaussian spherical surface. For that, what is the equation, Adnan? Phi equal to, for the flux, only for flux, phi equal to integral over the
Closed
closed surface of the sphere E dot
E dot ds.
E
Yes.
dot ds. ds is a vector. And one more point required here. Listen here. We have taken electric field intensity at the point P as E. E is the magnitude, direction is radially outward.
Yes, sir.
Okay. Now,
Yes.
if this distance is
Yes,
small
sir.
r, if this the point P, right now the point P we have taken, it is at a distance small r, and if r, E is the electric field intensity at that point, and all other point on this imaginary spherical shell is same distance r only, and it is uniformly charged, and due to the symmetry of electric charge and equal distance from that spherical shell, everywhere on this imaginary sphere E will be same. E same means E is a constant.
Okay.
So everywhere theta is 0, because here electric field will be radially outward, vector area ds also same direction, so angle between the electric field intensity and vector
Zero.
area will be 0.
Into integral of
Integral over the
surface
closed
into D.
surface of the sphere,
The sphere
E ds
D.
cos 0. E ds, theta is what?
0.
Cos theta, theta is 0 throughout the surface. What is cos 0?
Yes.
1.
1.
1. And this electric field intensity is constant everywhere on the imaginary sphere. E is same, so we'll take that E outside the integration. It is a constant. Then we have to integrate the closed surface as ds. If you integrate the closed surface of the sphere ds, that is imaginary Gaussian surface, means we are integrating this ds, or we are considering this imaginary Gaussian spherical surface is divided into infinite number of ds areas, infinite number of ds area, and adding all together, infinite number of ds area added together. That is the meaning of integral ds, isn't it?
Yes, sir.
That is the meaning of integral over the closed surface ds. So what will be the answer of that if you integrate for this imaginary surface having radius small r? Remember, radius is small r.
4 pi r squared.
Okay.
4 pi small r square.
4 pi into small r square. That is for
Yes, sir.
integral, surface integral of this imaginary sphere. The
Imaginary.
imaginary sphere is having radius small r, so the surface integral for the entire surface
Big
of this
R.
imaginary spherical
Small
shell will
r.
be 4 pi into small r square.
Mm.
So this integral over the closed surface ds will give the results E into 4 pi r square. E into 4 pi r square. Remember, 4 pi small r square, there are two r's here, don't confuse. This is the total flux coming out, isn't it?
Yes, sir.
This will take equation number 2. Take it as equation number 2. This is the total flux coming out of this imaginary Gaussian surface.
Yes, sir.
Now the total charge inside this surface, I am taking capital Q. Capital Q is taken as the total charge inside the imaginary. So this is the imaginary surface. Inside that, the total charge means the total charge on the original shell, isn't it?
Yes,
The complete charges on the original charged metallic shell is existing inside the imaginary spherical shell. So the total charge inside the imaginary spherical shell will be what? Already we have written here. Capital
Yes,
Q equal to sigma into 4 pi capital R square.
4 pi
So
R
remember,
square.
this R should not be. The net charge enclosed inside the imaginary sphere is equal to the total charge on the original
E.
sphere, that is Q equal to sigma into
Sigma
Mm.
4 pi
capital R.
which R square?
Capital.
Square.
Small r square or
Capital.
capital R square?
Capital R.
Capital R square. And take this equation as equation number 3. Now we can substitute equation 2 and 3 in 1. So next step, write down substituting equations 2 and 3 in 1. In equation 1, what we can write in equation 1? Instead of 5 we can put what? Okay, substitute that. Instead of 5 I am writing E into 4 pi r square, E into 4 pi r square 1 by epsilon naught times epsilon naught into the total charge, the net charge inside that. Net charge is how much? Sigma into 4 pi r square. Sigma into 4 pi r square. Capital R square. Now what will happen? 4 pi will cancel.
4 pi will
This 4
get
pi
cancelled.
cancel.
E
Then E equal to what?
sigma r
Sigma
square
into capital R
by
square divided by epsilon naught into
epsilon
small r
naught
square.
r
Isn't it?
square. Yes, sir.
Electric field intensity at a point outside the shell is equal to sigma into capital R square, that is the radius of the original conductor hollow shell, and sigma is the surface charge density of that divided by
Epsilon naught into
epsilon naught, that is the
Into
permeability of free space, into small r square, that is the imaginary
imaginary
radius of the imaginary Gaussian cylinder,
surface.
into r cap. What is the direction of r cap?
Radially out.
The direction of radius of the sphere. The same equation again I am writing in a different form, that is electric field intensity E at a point outside the E is equal to, instead of the sigma I am substituting the value. What is sigma actually? Total charge Q equal to sigma into 4 pi
R by
into
area.
capital R square. Okay. So
Yes,
sigma
sir.
equal to what?
Q by 4 pi r square.
Yeah.
Q by
Total
4 pi
charge
square.
divided by area of the sphere. That is 4 pi r square. That is the meaning of charge per unit area. Total charge by total area will give charge per unit area, 4 pi r square. Capital R square, that is the radius of the original charged spherical shell. Now in this equation for sigma, I am substituting this equation, capital Q by 4 pi r square. Then what will be the equation? For the sigma, instead of sigma, first I am substituting. For this sigma I am substituting. So capital Q divided by capital R square.
R square.
Okay. This is sigma value. And what is remaining then? Capital R square. Then divided by
Small
epsilon
r
naught into R square, small r square, into R cap
4
to give the
power
direction.
r
This
cap.
capital R square and capital R square cancelled.
Yes, sir.
Then this equation can be written as E is equal to, electric field intensity E is equal to 1 by 4 pi, there is 4 pi there, epsilon naught is there, only capital R squares are cancelled. So I am writing 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught,
Capital
Okay.
Q by R.
1 by 4 pi epsilon naught, Q divided by, this Q is remaining here, that is a total charge on the spherical shell, Q divided by, what is remaining in this side? Small r square. This is an important result. This, put it in a box,
Oh.
electric field intensity at a point. There is some similarity for this equation.
Yes, sir.
What is the similarity of this equation? Anyone explain?
Due to a point charge.
Good, very good. Electric field intensity due to a point
Due
charge.
to a point charge.
now,
charge.
now you just imagine, correct only. See, suppose this total charges here on this large metallic hollow conductor, hollow metallic shell, there are Q charges, total Q capital charges are there. Imagine all that charges I am concentrating at the center as a point charge. Got it? So if you imagine all these charges are concentrated at the center of the sphere, and then you take a point P here at a distance small r from that point charge, according to the first equation we already derived, electric field due to a point charge is given by what? 1 by 4 pi epsilon naught.
Yes, sir.
Yeah.
Yes, sir.
So what is the meaning of this one?
All the charges are concentrated at a single point.
Yeah. Meaning of this one is electric field at a point, due to a charged hollow conductor, spherical hollow conductor, is equivalent to electric field due to a point charge, such that the entire charges on the sphere is considered to be concentrated at its center.
Yes.
It means if you find the electric field intensity because of a spherical charged shell at a distance r from the center of it, it will be equal to the electric field intensity produced by a point charge if the point charge is equal to the entire charge on the surface of the shell. then both are giving the same effect. Got it?
Yes, sir.
So in exam,
Yes, sir.
this question came like this. The question was like this. You can remember the question. Prove that electric field intensity at a point at a distance r away from the center of a spherical shell and outside the shell will be equivalent to electric field due to a point charge with the same magnitude.